Okay, so this is going to be a video about the beginning of Unit 7. And Unit 7 deals with exponential and logarithmic equations. And we're going to talk about a lot of things in this unit. We're going to talk about properties, we're going to talk about solving equations, we're going to talk about relationships. We're actually going to get into some real-world conversations about money and compound interest. But to start, we have to understand what an exponential equation is and how it is related to logarithms. So an exponential equation is written in the form y equals a times b raised to the x power. And this is the first time in this class where we've seen the variable x be up in the exponent. Every other time it's been multiplied or added or subtracted or raised to a power itself, like x squared, but it's never been up in that exponential spot. And so we need to understand this new form of an equation, and it's called an exponential model. Now, like equations that we've studied before this, different pieces of this equation can tell us certain things about the graph. So some key information that we can pull from this equation is that our exponential model is either going to be a model of exponential growth or exponential decay. Now, exponential growth, when we graph it, tends to start low, and then as we move to the right, it shoots up quickly. So as our x's get larger, so does our y, very quickly. For exponential decay, we would expect that we would start up high and then it would eventually curve down very quickly. So a lot of the things that you're going to be asked to do in relation to exponential models in this unit is to be able to predict whether you can expect growth or decay. And there are parts of this equation that can help us determine that. So for growth, if your a is greater than 0 and your b is greater than 1, then we can expect growth. So an example equation for that might be y equals 3 times 2 raised to the x power. Our a is greater than 0 and our b is greater than 1. So we would expect this to represent some kind of a growth an exponential growth model. For decay, we still want our a in the equation to be greater than 0, but our b is either going to be less than 1 or greater than 0. What does that mean? Well, it's going to be a fraction or a decimal that's less than 1, essentially. So an example of this kind of an equation would be something like y equals 3 times 1/2 raised to the x power. Again, that x, to be an exponential equation, the x will be up in the exponent. But because our b is between 0 and 1, this will represent a model of decay, of exponential decay. As you probably notice, this model is approaching, getting very close to, but not crossing the x-axis. And for the parent model, or the parent function, we do have an asymptote to deal with here, and it is a horizontal asymptote, and that's usually located at y equals 0. We don't see any restrictions on the x variable though, and so we can say that the domain, or the x values that we deal with here, are all real numbers. All real numbers. Now, like other equations we've talked about before, this parent function can get moved around. In previous units, we've talked about stretch and compress. We've talked about horizontal shifts left or right and vertical shifts up and down. The same exact concepts we've talked about in prior units apply here. They're just in different places. So the A expresses a stretch or compress. So if the A is a fraction or less than 1, like between 0 and 1, we're going to see a compression. And if it's greater than 1, we're going to see a stretch. So A kind of controls how curvy these are, or how quickly they slant. The B in there is our growth or decay. So that's going to tell us what direction our line is curving in. Then, since our x is up in the exponent, our horizontal shift is going to exist up there too. And again, we're going to have a sign switch. So if we see something like x minus 1, that's a move to the right, and a plus 1 would be a move to the left. So it's always kind of the opposite of what you would think. Then, of course, a plus k would be a up or down movement. So an addition there would be a translation of the graph up, and a subtraction there would move the graph down. Now, a special note. Notice how the parent function has a horizontal asymptote at y equals 0. That's this line right here. K has the power to change that horizontal asymptote. So if K moves our graph down minus 10, this entire graph is going to shift downward 10 spaces. That means that the asymptote it approaches but does not ever touch also moves down 10 spaces. So K indicates our horizontal asymptote. So if it's minus 10 in the K, that's also where the horizontal asymptote will sit. Let's see. So this is a shift up or down, and it also controls the horizontal asymptote. H is a shift left or right. B tells us growth or decay, and A is a stretch or compress. Another thing that A can tell us, A is also in charge of the y-intercept. The y-intercept is always going to have an x coordinate of 0. And then A is going to be our y-intercept. Very exciting. So you can always just pull A right out of the equation, and that's always going to be the y-coordinate of your y-intercept. So an example problem, or an example equation, to kind of put all this in perspective, might be y equals 3 times 2 raised to the x plus 4 power. There's no k over here, so we can assume that our horizontal asymptote is still at y equals 0. This is a growth model because our b value is greater than 2. Now this y-intercept is going to move, because our graph is moving, 4 units to the left. So what we would need to do here, because this graph is shifted, we would need to plug 0 in for x here to solve for our y-intercept. So we would get 2 raised to the 4th power. That's 2 times 2 times 2 times 2, which is 16. And 16 times 3 is 48. So our y-intercept will be located at x equals 0 and y equals 48. And I hope you're seeing some patterns here. We have always plugged 0 in for x to solve for our y-intercept. So the y-intercept of our parent function would just be 0, comma a, because if there's nothing in here for h, like we looked at up here at the top, if we just plug 0 in for x here, anything raised to the 0th power is 1. So 1 times a would leave us with a y-intercept of a. But if we've got other stuff going on in the equation, we would need to plug 0 in for x and solve for what our y-intercept would be. It looks like we are stretching our graph out because our a is greater than 1. And that means that it's going to be a very skinny graph. It's going to be a very skinny L. Very nice. So we're not going to work with exponential equations very much in this unit, but it's important to understand how they are set up, because when we go to solve an exponential equation, we have to use logarithms to manipulate the equation to get the x into a solvable position. So in this lesson here, we talked about the parent function of an exponential model. We talked about how to identify growth and decay looking at an equation. We discussed that most exponential equations have a domain of all real numbers. That means any number can go in for x and work. But not every number can go in for y. That means we will have a horizontal asymptote at y equals 0. Translations can happen with an exponential equation, and when they do, they change the positioning of the graph. A is stretch or compress. It can also help us find our y-intercept, so we need to plug 0 in for x here and solve, and whatever we get will be our y-coordinate. We talked about the B was growth or decay. H here is going to be a left or right movement, and K is going to be up and down, so K actually affects where that horizontal asymptote lies. Then we talked about an example of what an equation might look like, how to locate the horizontal asymptote, identify growth or decay, stretch or compression, and then with this shift to the left 4 units, we needed to plug 0 in for x to solve for our y-intercept. And that is a summary of exponential models. In the next lesson, we're going to discuss the relationship between an exponential model and a logarithmic model.